Okay, so in competitive inhibition, here's your reaction diagram for competitive inhibition. The enzyme plus substrate making the enzyme-substrate complex competing with the inhibitor. So if the inhibitor binds, the substrate cannot. If the substrate binds, the inhibitor cannot. So it's one or the other. But here's the thing. If you have a high enough substrate concentration, you can outcompete the inhibitor. That's why it's called competitive inhibition. So by adding increasing amounts of substrate, you basically can achieve your same Vmax. So it takes a higher level of substrate to get there, but you can approach that same Vmax with inhibitor. So this is what the curve looks like. So this is your original curve with no inhibitor. In a Lineweaver-Burke equation, as you increase the amount of inhibitor, it takes a different level of substrate to be able to get there. But eventually you get your same Vmax, although the Km is different because it's an extrapolation of the slope of the line to be able to get your Km. So in a competitive inhibitor, the Vmax is the same and the Km is different. So different types of inhibition. If you are using an uncompetitive inhibitor, so here is our reaction diagram for uncompetitive inhibition. You have your enzyme substrate complex going to ES, and after ES binds, after ES is together, only then can the inhibitor bind. And then if the inhibitor binds, there is no reaction then possible. But if the inhibitor does not bind, you go ahead and still get your product being formed. So with increasing amounts of inhibitor, you are changing your Vmax and you're changing your Km, and you're basically getting parallel lines in this case. If you are using another type of inhibition, so remember, if we're looking at our different types of inhibition right here, here we have uncompetitive inhibitor. And an uncompetitive inhibitor, remember I said that the inhibitor is only binding after the enzyme substrate complex is formed. So first the enzyme substrate complex is formed, then the inhibitor comes in here, binds, and stops the ability of the enzyme to be able to make the product. And if you have a mixed type or a non-competitive inhibitor, the inhibitor can bind either the enzyme by itself or the enzyme substrate complex. So if you have a mixed inhibitor, which is also a type of a non-competitive inhibitor, in this case, you have enzyme plus substrate going to enzyme substrate, and you can have the inhibitor binding just the enzyme or the enzyme substrate complex. And if these two numbers are the same, you're going to get non-competitive inhibition. I'll show you that in just a moment. And if they're slightly different, that's when you get a mixed type of inhibitor. So basically, they're almost the same thing, just depending on the particular affinities right there for the inhibitor. So if you have a non-competitive inhibitor, you have this point right here. So you have this point being the Km. So in a non-competitive inhibitor, the Km does not change, but the Vmax changes. If you have a mixed type inhibitor, this meeting point is actually right here on the graph. So they're both changing, but it has this particular shape, which is a different shape than uncompetitive inhibitors are going to have. So just as a reminder, if you read the lab manual, you will see that we are using Cibacron blue as an inhibitor, and it has basically the same shape as NADH. So it's going to fit into the same space on an enzyme where the NADH fits, but we're not changing the concentration of NADH. The concentration of NADH remains the same. We're changing the concentration of pyruvate. So I want you to think about that in terms and put it in context when you do your lab work of what type of inhibition then is to be expected If it has the same shape as NADH, but we're not changing the concentration of NADH, we're changing the concentration of pyruvate.